everybody. So I wanted to kind of share this video. I wanted to post this video on the page because one, I really want to just build or provide a resource and kind of go maybe in detail on some things that I wasn't able to hit as much during class today. But also, I was planning to record the lecture and it didn't work out. The recording didn't work for some reason, so I'm going to record it here and work it out. So, without further ado, let's jump into it. So, first thing we're going to do is we're going to focus on intervals. Okay? Because we really want to start here before we even move into this, because this is more of a one-dimensional, one-direction thing, whereas this is a couple of directions, has a couple of pieces going on with it. So, which actually is built off of this. So, let's talk about intervals first. So, whenever I talk about an interval, I imagine I have a line, like so, which I might imagine that I have 2 points on it. Okay, so on the left, I have a point I'll call A. On the right, I have a point I'll call B. Okay, and I'm interested in finding, well, what are, I want to see every value that's in between those two. Okay, so what I do is I'm going to color this in a little bit, and I'm going to say, what's happening with those two values in between? So, with that, what we do is we call this an interval. This is our interval, and it has a wide selection of numbers to choose from in between it. Okay, and there's a few ways to represent this, or a few ways to look at this, because sometimes we may want to include the things on the outside, or we may not want to include the things on the outside. Okay, so I'm going to list a couple here. So we're going to have an open interval, closed interval, and yeah. So actually, let's go ahead and start here. Okay. So whenever I say open interval, this means that I have things in between, but I'm not necessarily including the things on the outside. Okay. So in this case, I'm going to kind of allow some open dots here. A and B are not included in this picture. Okay, so I'm going to say, in this case, how we write this is I'm thinking I want all values x such that a is less than x is less than b. Okay, we can use interval notation to write this, and the way we do that is I'm going to write a comma b, and then since these are both just less than strictly, I'm going to put parentheses. Okay, we don't include the letters. We use parentheses to mark that they're absent. Okay. What about a closed interval? Well, a closed interval is closed, right? So instead of leaving those spots open, I'm gonna color in those dots, and those are gonna be closed. So now I am gonna include those values. So looking at this as an equality, I'm gonna say a is less than or equal to all my x's is less than or equal to b. Just like that, okay? And the way to write this is similar to, in interval notation at least, is similar to this, except instead of parentheses, I'm going to use brackets, okay? Kind of a bit of sharper points to illustrate that I'm including A and B in here. Now, obviously, we don't just have to be restricted to open or closed. We can also take like a mix, okay? So these are both types are called half open intervals. Half open for a optimist versus half closed for pessimist. So we're going to stick with half open. So when it comes to half open intervals, right, the first one, obviously we can have a is less than x is less than equal to b, or we can have a is less than equal to x is less than b, right? So this is just a mix of these intervals, right? So on the first one, I'm going to have a parenthesis on a and a bracket on b, versus on the second one, I'm going to have a bracket on a and parentheses on b. Great. So when it comes comes to dealing with two numbers, this is all the options we have. However, this isn't all of the options we have, right? Because although I may only want to go to a specific value, what if I just want to go all the way this direction or all the way that direction, right? Well, I have the ability to do that, right? So let's ignore B for now, and let's travel all the way to the right instead, right? So now I'm interested in having all x values that are greater than a, right? Or greater than or equal to, depending. Obviously just greater than for now, but obviously we know how to include it if needed. Well, in this case, how I would write this, right, is looking at my line, A is on the left. So I'm going to put A as a left bit, and this is open, this is, there's no equals to on here, so it's going to be a parenthesis. Now, when I go all the way to the right, the way I denote that is I put infinity, right? That says I go all the way that way and I include everything that way. Now, when it comes to infinity, I always put a parenthesis around it. We never put a bracket around it. I do not bracket in the infinity because it's not always included, right? Especially in this context that we're not going to include it. Infinity is not a number, and so we're not going to be able to use it. All this says is I'm going all the way that direction. Okay, I'm going as far as I can. Okay, now what if instead of x is greater than a, that maybe I would like start at b instead now, and I'm going to go all the way to the left. Okay, well, so now I'm saying I want all values that are less than b. Right now b is on the right side, so I'm going to put b here, and then to mark everything to the left, I'm going to use infinity in it again, but this time it's negative numbers, so I need to put minus infinity. And so that's another way to write down that interval, right? To go all the way this direction, right? Finally, one last interval is I just say, well, I don't need to restrict where x is. I just want x is anything. I'll say x is any real number. Well, if x is any real number, then the interval notation in that case, right, is everything. Right? I want to include everything, right? So I'm going to include everything to the left, which is minus infinity, and I'm going to include everything to the right, which is positive infinity. Okay? So these ones are definitely going to come in handy when we're describing our intervals and stuff. But these are all the different forms that we can have it. Okay? So, the last thing I want to mention about this before we move on is that sometimes I might want to combine different intervals together. So they may not be connected, but I need to use both of their information, right? So let's say that, let's come back to our line, that I have a half open interval from A to B, and I have just a straight, completely open interval from C to D, right? And I want to include all these values. They're all significant, so I kind of want to bunch them together. Well, the way to do that is I want to write down each one, right? So in this case, A is open, so it's going to have a parenthesis, A, comma, B. B is closed, so I have to include that with a bracket. And then here, both C and D are open, and we're going to write this. Now, to say, well, I want to put those together, I'm going to use a U, kind of like a union. I'm pulling them together, okay? So this will be useful, of course, when we get to here, to basically say that it's okay to pull from here and here, and so I'm going to bunch them together. Great. So anytime you have two separate intervals, you can pull them together by using this U. Awesome. With that all being said, that is intervals. So with that out of the way, we're going to move on to functions. So the nice thing about recording on here is that I can erase this and you can still pause and write everything if I erase it too fast. So, okay, so intervals, we're done. Might come back to use that, but now we're gonna move on to functions. So, what is a function? Well, the book gives a pretty good definition. It might be a little weird trying to figure out what exactly it's saying, right? But let me just try to explain it by writing out a little bit here. So, a function can be taken of as something which I have some object, some group of things, and I want to put them into something. I want to put them into kind of like a machine. And when I put them into the machine, or in this case the function, it pops out something else, right? So it kind of takes one thing and turns it into another, right? Or it says, if I put this thing into this machine, this function, then it's going to give me this specific object out of it, right? Now, the way we look at this is I'm going to write y equals f of x, okay? We say this is f of x. So what that means is that I take x is my object that I put in, and when I run it through that function, that machine, it's going to pop out a value, and that value in this case is going to be y. Okay? Now, whenever we talk about this needs to be well defined, right? Because if I'm making something, right, or if I'm designing something, if I put an object into it, I should expect a certain result to come out. Especially in a, kind of a design world, I want it to work one specific way, right? So, ideally, if I put one x in, I should only get one y. I should get one y answer out of it, right? If I put f of a into a function, and I get b1, but I also get b2, that's a problem. That doesn't work. I shouldn't put an object into this machine, this function here, and get two different results. I should be able to predict exactly what that result's going to be. Now, if there's only one, if it only comes out to be one, in this case b, then that's good, right? I want to be able to plug in a certain value and it only spit out one other respective value, okay? And this is actually what it means to be, we call this well defined, essentially that it acts as it should. It's not giving us a whole bunch of objects when I put one thing in. Okay, so if that made sense, great. If not, let me take us to a graph. So I'm going to give a couple of examples. Let's look at a parabola. I'm going to call this, so this is y equals x squared, or f of x is x squared, kind of going with our function notation here. And we're also going to use a circle. Okay, now in chapter 1, we can see that the equation is of a circle is x squared plus y squared is 1. But it's kind of awkward to try to write this as we can't really write this in this form, right? Because everything's on the same side. But yeah, it's still an equation, we can still graph it. So, what is the difference between these two? Well, if I take a value, let's say here on this line, and I look at the graph, right? When I plug it into this function, right? It looks like I only get one corresponding value, and that's good. I only get one result, and I get nothing else out of it. However, when I look at this circle, what happens when I go to this value? Well, that doesn't happen. I have two options. I get two things. That shouldn't happen. My function shouldn't work like that. That's just, it's not a function. While we might build a graph and look at it, this unfortunately does not work appropriately as a function. And because of that, I can't use this. This isn't a function. I can't use this as a function. Now, might I be able to take a piece of it and use it? Absolutely. But in this case, this thing, because two values for this x, not a function. And that makes sense greatly. Now, this over here, though, is a function. Okay, so another way to look at this is you may have heard of the vertical line test. And this basically says that if I take a pencil, pen, my marker, an arm, hand, whatever, and I run it across the graph, right, my marker should only pass one point at a time as it moves across, right? For this parabola, there's no issue. It's only passing 1 point at a time. However, notice when I pass my marker over the circle, oh, I'm hitting 2 points. One here and one here. So that fails a vertical line test. So that means this is not a function, but this one does pass it. So that is a function. Okay. So that's the basic idea of a function. That's what we're working with. It sort of operates as a machine, right? So, and as with a machine, we have an input and we have an output. But in this case, we're math, so we're focusing on things called variables, right? We're working with variables. And in this case, there's two different variables. The one inside the function, x, is called the independent variable. Okay, now why is it called the independent variable? Well, it's called independent because it's independent of the function itself. I'm saying, okay, well I have all these things I can choose. Let me choose one of them and put it into the machine, right? There's no dependency. I'm not dependent on the f to give me that value. I already have it. I just have to put it in, right? So that's called an independent variable. So if x is the independent variable, that must leave y to be the dependent variable, right? So the only way I get that specific y is because I had a specific x that I put in to give me that y, right? It's dependent on the x. X can do what it wants, but y has to do whatever the x allows it to, right? Now, you might be wondering or thinking about, is there, can I do whatever I want with this, right? Can I really use any x I want? And can I really what y's could I get, right? Could I still try to get a specific y? What options do I have, right? And to answer that question, we have two terms that associate with this. When it comes to the independent variable, x, we call all the possible x's that we can plug into the function, we call that the domain. Right? So if it can be put into the function and nothing is a problem, then it's in the domain. It's allowed. It's allowed. The machine can take it. For the dependent variable, that domain is going to produce a specific set of values, and that set of values is what we call the range. Okay, so let us take a moment and study this. Right? Let's take a look at this concept and try to understand what's happening. Okay? So we're going to look at a few just basic functions and try to establish what's going on. So, I'm going to give us four functions. The first function I'm going to look at is y equals x plus 2, y equals x squared minus 1, y equals 1 over x, and y equals the square root of x. Okay, so now whenever it comes to each of these functions, I want to ask, well, what's the domain and what's the range? Okay, so when it comes to y equals x plus 2, right, let's think about this graph. I'll kind of draw it a little bit on the side here. This is just a line. It has a y-intercept of 2, and it just has a slope of 1, so it's going to look something like this. So, is there any problem with this? Is there any x that will give us an issue? Well, No, each time, I mean, x is just there. It's not really dividing anything. It's not really inside anything. It's just by itself, right? All I'm doing each time is adding 2. And as far as, as we're dealing with our real numbers, it's completely fine to add 2 to any of them, right? So I can take any x value that I want. Okay, so in this case, the domain of my function is going to be all real numbers. It's going to be all of them, right? Which we saw from the interval. Now we want to, this is where our interval part is going to come back in. That when we're saying all real numbers, I'm going to write this as minus infinity to infinity. Next comes, let's see, actually, maybe we'll continue on with, well, let's go to the range directly. Okay, so now that we know the domain of this function, I want to know, well, what's the range of this function, right? So, so I can plug in any real number I want to, right? So in order to kind of think about the range, I think, it's something that you kind of want to, we can look at a little bit through these problems, kind of take some basic value of y, so I say that I want to get this value of y, what x do I need? And that'll kind of help us to understand this concept of the range and how to find it in general. So let's look at this problem, right? So let's say that I want y to be some b value. Okay? So we want b. I want y to be b. So I need to that question I need to ask is, what does x need to be to give me b? Well, that's pretty easy, right? X just needs to be b minus 2. Great. So if I want to get this specific value, right? So for example, if I want to get, if b is 7, if I want to get 7, then I just need x to be 7 minus 2. I need x to be 5, right? Because then 5 plus 2 is 7, right? And so that means that, like, as long as x is this b minus 2 value, I can get whatever b I want, right? I can get this value that's within the range. Now, x goes from minus infinity to infinity, right? So, and we can even look from this picture, right? I can get all sorts of these values, right? If all I have to do is add 2 to any number within this domain, and I get a specific y value, right? So, again, I'm going to get every single real number. This range consists of every single real number. So because of that, the range of this function is also going to be minus infinity, infinity. If it's in this range, if it's in this section, I can get it out of the domain, right? If I want 100 billion and 2 in my range, I just let x be 100 billion, and that'll give me what I want, right? So it works out. Now let's talk about x squared minus 1. So x squared minus 1, again, the domain, it's x squared, right? I can take any number and square it. If it's positive or it's negative, I can get whatever I want, right? So that's great. There's no issue. So the domain here is going to be minus infinity to infinity. Now something different here happens with the range, right? Because in this case, it really looks like I get everything here. But let's think about this graph. So this is the graph of x squared, right? But notice I have this minus 1 in the end. So that means I need to take every value of x squared and bring it down by 1, right? So whenever x squared is, when I put 2 into x squared and get 4, I need to bring it down 1. So now it's only going to be 3. And so now I'm going to get something that looks like this. It's kind of hard to see my picture from here, I understand, just based on how small I'm drawing it. But notice that it stops at a certain point. It doesn't go all the way down like this graph does. It stops, right? So we can't get everything, right? There's a lot of negative values I can't get, right? Let's think about x squared. X squared is always a positive number, right? If I take 0 and I square it, it's 0. if I take a positive number and square it, I get a positive number. And if I take a negative number and square it, I also get a positive number. So this always has to be greater than or equal to 0. Even though there's this -1, that's only going to bring that down by 1, right? My range is a lot more limited than my domain is, right? So clearly, right, if I put 0 in here, I'm going to get -1. So -1's allowed, right? But beyond that point, right, once I put in anything but 0, it's got to be bigger than that, right? And I go all the way up. So my range in this case is I can include -1, because I'm able to get -1 out of it, right, when I put 0. But every other value is bigger than this. So I have to go towards infinity. Okay, so that is the range of this function. Okay, so that makes it a bit different than x plus 2, because it's a bit more restricted. And you're going to find this similar pattern when I'm dealing with polynomials of different degrees, right? If the degree is odd, right, so this is an odd degree, and as we go higher, if I have an odd degree, so x cubed, x to the 5th, x to the 7th, etc., that's going to be something like this, most likely, right? However, if I have x squared, x to the 4th, x to the 6th, right, that's cutting off a good portion of my graph. Everything has to be above that, because that term is going to be positive. So what that means is that my range is going to look something like this, even if I can't take all values. Okay. Now we're left with these other two options, which are 1 over x and the square root of x. So 1 over x and the square root of x. Let's see. Can I put anything I want to inside 1 over x? Well, it seems like I can put most numbers in there. Like, 1 would be easy. 2. I mean, most numbers I can think of could probably be in there. But there's one big issue that comes with this function and other similar functions to it, right? One thing we learn very early on that's a big no-no is dividing by 0. When we divide by 0, that's we don't get anything. It doesn't tell you anything. We can't get any information out of it, right? So if I let x be 0, that's a problem. That's not going to work. That doesn't give me anything. There's no output from that, right? So 0 is not included, right? But everything else is fine, right? Even if it's something that's pretty close to 0, it still will give me a number, right? So really, it's very much the same as, like, we get most of these real numbers, right? So I'm going to get minus infinity, infinity, but there's one I can't include, and that's 0. So I'm going to have a couple different intervals, right? One where I don't include 0 on the left side, and I don't include 0 on the right side. But I want to include all this as my domain, so I'm going to put a union in between to let me know that, hey, I can take any of these values from either side. Cool. Now, with that being said, we have to ask about, well, what's going on with the range, right? Well, to see that, let's kind of go back to our B thinking, right? You could also draw the picture if you want to. The picture of 1 over x is going to look something like this. But still, it might be exactly hard to tell a little bit with our range, right? So, let's go back again. Like, let's say I want y to be b, right? I want to get some b value out of y. Okay. So what I do is I'm going to let b be equal to 1 over x, and I need to say, okay, well, what x do I need to get? Do I need to put in here that'll give me that specific y that I want? If I want to get b, I need to figure out what x is, right? So the way we do that, right, is I'm going to multiply both sides by x. So I get b times x is equal to 1. And then if I want to solve for x, right, because I want to see what the x value has to be, x is going to be 1 over b. Good. So if I want to get b, I just need to put in 1 over b for x, right? So, again, so many values of y are allowed here, right? I can put any b in here and get something logical. I can get something nice. However, there's still one big problem, and it's the same problem from before. always happen with these sort of rational functions, but in this case it does end up being the same, right? Again, I cannot divide by 0. So what does that mean? That means that b cannot be 0, which in turn means that y cannot be 0. But y can be anything else at once. So what does that leave us with? It leaves us with a range that's, in this case, exactly the same as the domain. Okay. And let me preface this, or let me just add on again and say this doesn't always happen that they're the same. But anytime you're dealing with a rational function like this, you will typically deal with some sort of intervals like this potentially, where there's going to be one value that makes everything, that kind of breaks everything, but everything else kind of works out. And so you just need to make sure to not include that one, but everything else is okay. Cool. And so sometimes this might be 0, 0, this could be 0, 1, 1, 0, 2, etc. In between, but follows the same format. Okay. Let's talk about the square root of x, right? As our final one, right? Can I put anything I want to inside the square root of x? Well, no. I mean, I can put 0 in, I can put positive numbers in, but I can't put negative numbers in, right? At least in this class, we're not dealing with complex numbers. We're not dealing with I can't put -1 inside for x, right? Because that's not a number that we're going to be using for this class. And because of that, I need my domain to be restricted. I can't include any negative numbers, but 0 is okay. So I can include 0. And everything else, any positive number is okay. So I'm going to put infinity. So this ends up being the domain of my function. Great. Now, what about the range? Well, the range is going to be whatever this domain kind of yields us, right? So let's see what happens, right? So if I'm plugging in any number from 0 to infinity, right? Well, what numbers get spit out of the square root of x, right? We might want to say plus and minus values, but that violates the function idea, right? That violates everything we just defined about a function, right? Because a function should only spit out one value, not two. So anytime you see a square root, unless the sign in front is different, we're going to assume that the value that comes out is a positive number, okay? So if I'm doing the square root of 4, for example, it would only give me 2, okay? So, again, 0 I can put in, and that's okay, it just gives me 0, right? So 0 is included again, and this always has to be positive, right? And really, I could go back to this thinking again, right? Using b, if I put b equals the square root of x, I would see that x would have to be b squared, right? But all these x's are positive, so they can be written that way. So, again, I could include all these positive numbers. So, I'm going to go from 0 to infinity again. Okay. So here's the 4 kind of basic ideas that you're going to deal with as we go through, as you go through your homework problems especially. And they're going to vary a little bit, but the same idea holds for you. So try to follow this ideal here and see if you can kind of shift it or mold it to kind of match whatever you need in the situation. So, with that being said, let me provide maybe a couple more examples real quick of this on the side, just to look at. So let's see. Let's talk about a couple of functions. The first function I'll talk about is f of x is 1 over x plus 2, and g of x is the square root of x plus 2. I just have infinity with x plus 2, I guess. I just think it's a nice one to use, so we'll go with that. Okay, so what's the domain of this function? Okay, I encourage you to try to think about this and try it out for a bit before I kind of finish going through it. But same situation applies with the other rational function. And now I do not want the bottom to be 0. So, if the bottom can't be 0, well, that leaves me with x plus 2, right, cannot be equal to 0. So what can't x be? X cannot be equal to -2. But, as before, any other number works. So, to write the domain of this function, I'm going to write, it's going to be negative infinity to -2, and union with -2 to infinity. What about the range? Well, right, again, we could try to set up the b situation, you know, kind of think about this random b value that I want. X plus 2, which ends up being x plus 2 equals 1 over b, or at which I get x is 1 over b minus 2, right? So if I want to get a certain b value, this certain b value for y, I want to put in this value for x, right? But the same situation holds, right? B still can't be 0, but b could be anything it wants to, right? So b can be 0, but b can be whatever else. So, just similar to before, I'm going to have negative infinity 0, union with 0 to infinity, right? Now here's what I was talking about, and that these two numbers are different, right? So they don't always correspond to each other directly, right? Another way, as I said, to look at this is to graph the function. So I'll kind of use this space to graph it. But remember that, as we talked about with x squared minus 1, that basically takes all of your graph and moves it up or down. But if I have a certain value with my x, right, and not just on the side, then that means that actually moves my graph left or right. If I have plus something with x, then that moves my graph to the left. And if I have minus something with x, that moves my graph to the right. Okay, because it has to adjust itself, right? Because typically, if we're talking about the graph of y equals 1 over x, which I'll denote with dotted lines here, the point 1, 1, we have the point 1, 1 on this graph, right? Well, how would I get 1, 1 on this graph? Well, to do that, I would have to let x be minus 1 instead, right? Or I guess, how do I get 1 in this case? I need to let x be minus 1 instead, right? But that's 2 away from where it was. So that means that, minus 1, all of my graph gets shifted over by 2. So originally we couldn't have a value at x is 0, but now we can't have a value at x is minus 2. So we're going to get something that looks like this. Now you'll still know, right, kind of following along with this range, that it can't be 0, but it could be anything else it wants to. So it's perfectly allowable. Okay? Now we come back to the square root example. Again, we don't want the inside thing to be negative, right? Which in this case, so we don't want x, we need x plus 2 to be greater than or equal to 0, right? We don't want it to be negative, so we need x plus 2 to be greater than or equal to 0. So what that means is that x must be greater than or equal to minus 2. How do I write this in interval notation? Well, I am going to take -2 and box it in and go to infinity, right? Just as we saw on the last page with on the kind of last board with 0, and using that same form that we saw earlier when we were talking about intervals. Okay, what about the range? Well, what happens if I put -2 in? I get 0. What happens if I put anything bigger than -2? Well, I get all sorts of other positive numbers. So I can get 0 and I can get a positive number. So this is going to be 0 to infinity, right? Again, they don't necessarily agree, but that's okay, right? They don't have to. So these are those domain arrays for those problems, and hopefully that'll be a good guide as you work through your homework. Good, okay. 3 more topics, quick topics, before I kind of end this video. And so let's cover them real quick. So, topic number 1. Okay, function notation. Okay, so you've been seeing me write f of x a lot, and that's okay, it's kind of the most general form, right? But we don't have to use f. I could use g of x. I could use a bigger f. I could use a bigger g. I could use some crazy letter like phi. But here's the thing. X doesn't even have to be x. I could use another variable, right? It doesn't matter, right? I use x, I call x my independent variable, but if x isn't necessarily the variable I'm using as my independent variable, it's not like everything's going to break down. It's completely fine, right? I could put, I could say f of t, g of v, f of s, g of triangle, v of smiley face. Anything's possible, right? I can use anything I want to, just as long as I'm consistent, right? So, the question I have for you, and actually a similar question the book poses, what is the difference between this function and this function? What's the difference between these two functions? Well, other than the second function probably getting you laughed at because nobody would use pizza as a variable generally, they're the exact same thing. There's nothing different about these. I use different notation, but it's still explaining the same thing, right? In this case, x is my independent variable, and in this case, pizza is my independent variable, right? I can use whatever I want to describe this, and it all works out. So, this is okay, right? So as we continue through the course, and if you see t's being used, v's being used, if you see f of x and g of t and all these things, don't be stressed, right? We can change which one we use, right? We're going to use basic ones, but we can allow for different forms like this. Okay. Topic number 2. I said that one was quick. Topic number 2. Is going to be composition. Okay, so whenever I'm talking about composition, and I should say composition of functions. Okay, what if I'm not satisfied to run through the function once? What if I'm not satisfied to run through the machine once? I want to run through it a couple times. Or what if I want to take that object and run it through this machine, and then take the object that it gives me and put it into another machine? I'm allowed to do that. It's okay. And we call that process composition, right? So I can have a couple different functions. So let's say I have f of x is x plus 2. Hey, let's bring it back. Why not? And we want g of x to be the square root of x minus 1, let's say. Cool. Okay. So let's say that I want to take a value and I want to plug it into g and then put that value into f. Well, the way that we write that is I'm going to notate that as f of g of x. So this is a function composition, right? So what this is going to look like is I'm going to have f. Another way to write this, I guess, essentially is to say that I have my function f, and in place of x, I'm going to plug in g of x, right? So this and this are the same thing, but they are both this idea of this composition of a function. So I'm going to take my function, which is the square root of x minus 1, right? This is g, I'm going to put it in here. So I'm going to have f of the square root of x minus 1, which is going to be, right? I just take that x value and I put it in for f, right? Now, I might cover some more examples at the end, just kind of hammer in this idea, right? is it correct if I just take the square root of x and put it in for x plus 2 and then subtract 1? Well, in this case, it sort of works okay. It will technically be correct, but not for the right reasons. Right? Whenever I plug in the square root of x minus 1 into my function, I have to put it in for the x value. So in place of x, I'm putting the square root of x minus 1. And then I add 2, which in this case is going to be the square root of x plus 1. So that one worked out. However, one that's not going to work out so easy, if you tried it the wrong way, is what if I want to compose it the other direction? So instead I want to I want to go into the F machine first, and then go into the G machine. Well, to write this, I'm going to write G of F of x, right? Which is going to be G of x plus 2, right? Which again, if I just said, I'm just going to write down the function, right? Put in x for x, and then add 2. Well, this is clearly definitely not going to be right, because this is not going to be the same thing as that, right? So this is incorrect. I need to take x plus 2 and put it in place of x. So I'm going to take the x plus 2 and put it in for the x right here. So that's going to give me the square root of x plus 2 minus 1. So that is g of x, right? Now, as I said, we could run through the machine twice as well, right? So I could just do f of x. Or I could do g of x. I'll stop it. I'll do just f of f right now. But when I do f of x, I'm going to take f. I'm going to compose f with itself. So I'm going to put f of x inside the function. So I'm going to have f of x plus 2, which is going to end up being x plus 2, right? Because I put x plus 2 in place of x here, plus 2, which simply just ends up being x plus 4. Cool. So here we go. Number 2 is composition of function. Okay, so real quick, while I'm thinking about it, and while we're kind of on this topic of where to plug in the values, right? Let's take a moment to kind of practice that before we get to our final argument. So, if I gave the function f of x is equal to the square root of x minus 3. Right? And I'm asked to figure out what is f of 3. Well, that would just be the square root of 3 minus 3, which is the square root of 0, which is simply 0. What if I want f of 4? Well, again, I take that 4 and I put it in for x, and so I'm going to get the square root of 4 minus 3, which is the square root of 1, which is 1. Now, let's do something maybe a bit more abstract. Let's do f of a squared plus 3, okay? And I want a to be greater than or equal to 0. So, let's just say, just to make this easier potentially. So, when I do a squared plus 3, that's going to give me the square root of a squared minus 3, and then plus 3 on the outside, right? No, we don't do that. If it seems like I'm stressing that a lot, I am, just because I've seen this so many times, and I'm really just trying to prevent it as much as possible. So, whenever I'm plugging into my function, I have to take everything that's inside, that's being put into the function, and substitute it for x. So in this case, to write this correctly, I need to do the square root of a squared plus 3 minus 3 inside, right? Now I could take that out with parentheses, and plus 3 minus 3 would cancel, leaving me with the square root of a squared. But the square root of a squared is just a. And especially if a is greater than or equal to 0, then we're good, right? Now, what if I didn't know a was greater than or equal to 0? What if I didn't have that condition? Well, we always need the square root to be positive, right? We talked about that earlier. It should only spit out one value, right? But if a is negative, right, then this definitely can't be right, because the square root isn't going to give me a negative number. So what I do is that anytime I think the square root of something squared, I'm going to do the absolute value of it, right? Now, again, let me say, if a is greater than or equal to 0, then this is unnecessary, because what's the absolute value of 0 or a positive number? Well, it's that thing. But in general, I would need to do the absolute value. If I wanted to include, if a was less than 0, then I would need to do the absolute value of the number. So, okay. Finally, let's see. Do I want to do another? I think I'll be good. Well, actually, I got an idea. I got one more. Let's do f of x plus h. Okay. Again, what's not correct is putting the h on the outside. No. What is correct is putting x plus h together in for x minus 3. Now, that really can't simplify too much farther, but this is actually going to come in handy later on, so just wanted to kind of get that across. Cool. Okay, sorry for that little aside, but I think it's important to practice that. Some of the homework problems are involved with that. Okay, finally, we're going to talk about piecewise functions. Okay, so I've talked about functions already, which are all connected, all do the same thing, all the same shape, right? But sometimes, depending on what object I put into my machine, into my function, right, I might want something different to happen, right? So if I put a negative value in, for example, I might want something to happen. But if I put in a positive, I want something else to happen, right? You know, the easiest, probably one of the easier ways to look at this is just like, or easier examples of this is to say, if a number is negative, I just want it to be 0. But if the number is positive, I want it to be 1. I want it to actually be something besides just 0, right? Another way to look at this is or another example, right? Maybe a crazier one, is to say, okay, I want everything over here to be doing this. I want everything here to be doing this. And I want everything here to be doing this. Right? Which is a bit stranger of a construction, but if you so desire, you can create that function, right? And so the way that we do that, right, is I say f of x or g of t or what, whatever you're using, and I can name different things to happen depending on what part of the graph I'm at, right? So I can say, for example, maybe that I have the graph is going to be x plus 2 whenever x is greater than, actually let's say when x is less than 0. And I want x squared minus 1 when x is greater than 0, greater than or equal to 0. So what that would look like, right, is on everything to the left of the y-axis, right, is going to look like x plus 2, right? So again, this is a line with a y-intercept of 2 and a slope of 1. So we're going to get something that looks like this. What about this side? Well, it's a parabola, x squared, that's moved down 1, right? Which now, notice, we're including 0 here. So we do need to include whatever the 0 value of this is, which would be minus 1. But we don't include the value up here, right? Because 0 isn't included here, so we can't include 2. So, but here, anyway, coming back to this, I have a parabola, x squared minus 1. So, I'm just going to draw the right side of that, right? Because I only have the right side. And so my graph is going to look something like this, right? And and so our result looks like this. Now, is it possible that I could kind of combine these two graphs together? Yeah, absolutely. I could, maybe instead of x plus 2, I could say x minus 1. What would that do? Well, I would have a y-intercept of 1 now, but that would act like a line, right? So now it kind of looks like my graph's a bit more connected, right? And so there's kind of a smooth connection point now. However, this isn't completely necessary. We don't always have to do this. You can, more often than not, we're going to encounter situations where, let me get back to 2, where the graph is going to be split in this way. Okay, so as a final check, to make sure we kind of understand what's happening here, what is f of minus 1? Well, where does minus 1 fall into? Is it in the x is less than 0 category, or is it in the x is greater than or equal to 0 category? Well, it's very clearly an x is less than 0 category. So I'm going to put that into x plus 2. So that's going to be negative 1 plus 2, which is 1. Okay? Now what about f of 1? Well, f of 1 is in the x is greater than or equal to 0 category. So I have to plug it into x squared minus 1. So I'm going to get 1 squared minus 1, which ends up being 0. Finally, let's look at f of 0. Ooh, now this is the teetering point, right? But which one includes 0? Is it the x plus 2 part or the x squared minus 1 part? It's the x squared minus 1 part. So I'm going to get 0 squared minus 1, which is going to be minus 1. Cool. So, funny enough, I didn't actually necessarily plan it like this, but we did. We put negative 1, 1, and 0 in here, and we ended up getting 1, 0, and negative 1 out in some fashion. Well, but there we go. There's a good example of a piecewise function. And really, you could have any mix and match, but it's really important to focus on what the x values are and what your functions are at the time. And it's always good to graph, so really practice trying to graph, and I think chapter 1 might be a good help for some of that. So, okay, well, I think that's all. I hope that this video helps, especially for those that weren't able to make it to the lecture due to coronavirus. Thank you all for watching. Please message me or come to my office hours, or just get a hold of me if you have any questions or concerns. I'm really looking forward to continuing to teach you guys and really get into the calculus part. This really isn't calculus yet. We're going to start that on Wednesday, and I think it's going to be enjoyable. So thank you all. Hope you have a wonderful night, and yeah, I will see you on Wednesday.